Okay, so chapter 8 is development and use of gauge block. So in measurement instruments, precision is the ability to divide into small increments. Accuracy, on the other hand, means adherence to a standard. Again, don't forget standard every time we talk about accuracy, and that's all parts made to a standard so they can be used in predictable relationships to each other. And the gauge sticks, they were first used in Sweden in the beginning of 18th century to transfer the measurement from craftsperson to manufacturing. And go no-go gauges were used later in 1890 in rifle production. So this is Carl Johansen, and he invented gauge blocks and system of block sizes for standardization and measurement. So here you can see the gauge blocks. Our gauge block set in the lab is smaller and it's just for education purposes, and this is for real, and they're very expensive. So when he built it, he started out with first block, and then he simulated the equations to derive all other blocks in the set. So the first inch set. So when you take a look at it, you're going to see the inch set on this side is 2.5 times larger than the smallest metric block. So here's your first series, 9 blocks, second 49, third 49, and then the fourth series of 4 blocks. Okay? And you can see the increment increases from here all the way to here. This side is your inch block, and you can see the first series 0.1001 inch all the way to the fourth series is 1 inch. Okay, here is like 1.001 millimeter all the way to 25.25 millimeter. So however you measure it, you're going to see the smallest block in the matrix set is 1.001 millimeter, and it equals to 0.0394 inch. Okay, so the discrimination of matrix set equals 0.001 millimeter, which is actually 0.0000394 inch. Okay, so light is a length standard. This is a type of supposed to be introduced by Albert Michelson, and we use light as a measurement, and it is a standard, a length standard. And the number of Cadian element from periodic table, so we're composed of these elements in different structures, including in the human body system, is actually come from C, H, O, N, and trace elements from the periodic table. So we're nothing but a systems composed of these particles, the same thing as that. So the number of Cadian wavelengths that correspond to the length of the meter. Okay. So here we're using the length as a standard of measurement. Okay. And here in this case, light is the length standard. So when you take a look at it here, you're going to see how very small that is going all the way. And then here is 0.01. Then we have come into 25.4 millimeter and then go all the way up. So when you take a look at the color composed in the light, you're going to see it from red all the way to violet, your rainbow. And then you can be able to measure the length in meter and also in inch. So here you can see 10 to the power minus 8. So that's very, very small length. Okay. And then on this side, the same thing, 10 to the power minus 6 inches. So in order for us to be able to measure very, very, very long distances, like from here all the way to some other planet, we use the light years. And here light years is nothing but it's just a way to measure the distance. Okay. So a standard of length is nothing but a physical thing, and it's going to define the unit of length. And the unit of length and standard of length, especially with light, when we use light, they're the same. Okay, the unit of length and the standard of length, they're the same. Because it's very difficult to form a standard, especially when you're measuring with light. So here, if we review the unit of length, then we should remember the standard of length is your international prototype meter. So here, the standard of length is your screw thread in your micrometer, and then the unit of length, the graduation on this barrel, and the thimble. So for light, they're the same because the standard of length, the wavelength of one particular color of light, is the unit of length, wavelength, again, of the same color of light. Okay. So gauge blocks, you have already seen many of them in the lab, and they're very flat, okay, simply flat and parallel surfaces. And using light waves, we can definitely determine the precise, also accurate separation of gauge block surfaces. So here you can see the gauge blocks. This is your surface finish, and this is your physical properties. And here, the number that I told you to write that down in the lab is your identification number. It tells you its measurement, okay? And then the metrological features on this side is your functional features. The measure plane, this is your axis, and we call the line of measurement is any perpendicular line, on the surface. And this line is your reference surface, okay? And all reference surfaces are totally parallel to each other. And this is reversible reference surfaces. And here is your reference plane, and this is your measure plane, okay? So the total length equals the sum of your individual length. So here is your gauge blocks. So the total length is the same as the sum of each block length, okay? It's a simple combination. You sum them up by stack them up together. So that's how you measure by using gauge blocks. Arithmetical progressions. I think some of you have already learned that in K to 12, especially in high school. So he used arithmetical progressions, so in which the need to combine the individual lengths and have the result fall within a standard tolerance. So each piece does not have an individual tolerance at all. So what does it mean? Example, if a precision device was being measured to plus or minus 0.05 millimeter, plus or minus 0.002 inch, that's your tolerance zone. So all the parts will have to meet the same tolerance. So each part does not have an individual tolerance. Okay, we use the combined one. So here's your gauge block set, and you've got 4 series. Series 1, and then series 2, and series 3, and then your series 4 in the set. So they combine to form any dimension from 2 millimeter all the way to 202 millimeter. Okay, in steps of 0.1001 millimeter. So that's your graduation or discrimination for a total of 200,000 combinations you can make out of that. Okay, so it's very powerful combination set. So if you think about, I want to measure 44.051 millimeter, then you're going to use 25.00 millimeter, okay, and then you're going to use 12.50, 4.50, 1.05, 1.001, and add them up. So you're going to get this dimension total, okay? So physically, you're going to stack these blocks up. So that's how you do the measurement. So here's your gauge block materials, and the characteristics of gauge blocks are they're made from something accurately sized and finished, and they're stable and not change size of their own accord. They can withstand considerable wear, and they're practical, affordable, and also wear and corrosion resistant. So here, gauge block manufacturers, our textbook, we use the Mitutoyo, but there are also other companies, okay? And they're very competitive to each other. And here you can see in this table, gauge blocks belong to the precision measuring tool. So macro geometry, it means nothing but large general shape of a part which can be measured easily with instruments. Micro, on the other hand, means minute analysis of shape, okay? We're analyzing very, very small shape that cannot be measured with high precision for accuracy. So microgeometry features are flatness, your parallelism, your straightness, your roundness, and the surface finish. And we usually use the double disc grinding process, okay, in mass production of flat precision components, and that must meet the high specifications for dimensional tolerance of flatness and parallelism. So devices like this. Okay. Surface topography definitely affects the use of gauge blocks. That's because surfaces have conditions like roughness or waviness, flows, and lay. So definitely surfaces affect the use of gauge blocks. So when you take a look at it here, you see the surface finish consideration. This is a very exaggerated picture, okay? You can see the floor right here, and this is your roughness height, little height right over here on the surface. And here is your lay, and here is your roughness width, and then this is your waviness height. Okay, here you can see the waving. That's right there. So roughness is finely spaced surface irregularities in a consistent pattern produced by machining or processing. Waviness is an irregular surface condition of greater spacing than roughness, usually caused by deflections or vibrations, not by the cutting edge. Floors, so right here you can see another irregularity, and floors, they do not appear in a consistent pattern, okay? Lay is the predominant direction of surface pattern. So roughness and floor, they're different, but this floor, again, they don't follow consistent pattern, but roughness, okay, definitely they do. I'm just trying to tell you that the gauge block surfaces, they definitely have a very high degree of flatness, and roughness affects the appearance of the surface, and we always think of only it in surface condition, okay? So here you can see the comparison of surface finish. It shows the exacting requirements for your gauge blocks. So when you think about a good surface finish, we don't go by the smoothness of the surface, because the surface may be smooth, but that doesn't mean like it has a good surface finish, okay? So the top drawing here show that an irregular surface or poor surface may have better reflectivity than a good surface finish. So the bottom drawing shows a reason for that. So here is your A, and then your B, C, and D. Then here is your reference plane. So when you look at the A, you're going to see peaks right there, 12 of them. And then B has 2, and C has 6 of them. And D, a lot of them, yeah. So here we're looking at the reflectability, and they vary. But flatness, they don't vary, okay? So here just trying to show you that the irregular surfaces or poor surfaces, they have better reflectability because the surface area is more, okay, it's more than a good surface finish. Surface finish was specified by RMS, we call that, and that's nothing but your met root mean square. And that method is definitely inadequate. So now we use the arithmetical mean or average. So here surface finish is measured by the height of the creases from the average, and these examples show that this does not fully describe the surface. So here A, and then B, and then C. And you can see the reflective surface right there. So E here, there are 3 peaks right there. And right here, D has more peaks. And here is your light, and here is your eye. And you can see reflecting. You can also see they're reflecting. But this side for E has more reflectability than D, okay? But for surface finish, D is better because they are definitely regular peaks, okay? And the light rays are evenly distributed. Where is actually proportional to the surface finish. So the larger the surface area, the better the load is distributed, and the lower the pressure on the surface of the block. So each minute scratch, okay, here you can see the scratch on the surface reduces the surface area. Look at this, see, you can see the scratch right there. So every time you have a scratch, the total surface area reduces. So here you have little scratch. So C has more surface area than A or B. B has, see, look at that, very, very deep scratch. So therefore, B loses more surface area than C and A. Gauge block grades. Well, precision gauge blocks, they're fundamental to dimensional quality control. Okay, so there are 5 gauge blocks under ASME B89 standard. Again, we follow the ASME standard. You just need to know the name of it. Nobody is going to come and ask you. There are still there are many different standards, and again, it depends on where you're going to be working and what that company is going to use. Okay, just follow whatever manual they have for the standards. So here you can see as an example ASME. You can see the deviations and tolerances for gauge blocks. Okay, 0, and then grade 0, 0, and then 0, grade AS1, and then AS2. They give you your tolerance, your plus and minus, your flatness and parallelism, all the way for different grade. Okay, so that's in a metric system, because in millimeter metric, again millimeter, don't forget that tolerance expressed in microns, because 1 micrometer is equal to 0.001 millimeter. Okay, micron is 10 to the power minus 6. Milli is 10 to the power minus 3. Here you have 1, 2, 3, so it total is 0.000. Okay, for micron is 10 to the power again minus 6. And this is your length of block in millimeter, all the way from 10 all the way to 250 millimeter. Okay. Anyway, that's an example for deviations and tolerances for gauge blocks, and the standard again is ASME. So here is just an example of your English system. So when you pay attention, you're going to see millimeters now in inches. So that's tolerance expressed in micro inches. Micro, again, here is a mu, and then inch. So we call that micro inches. 0.0000001 inch is equal to a million of an inch. Okay, because there's 6 right there. 6 zeros. 5 zeros and 1 is 6. Sorry, I called like 6 digits, alright, million. The size and shape, the 2 most used gauge block shapes and sizes are rectangular, we have seen this in the lab, and square blocks. So the square may or may not have a center hole. Both of that shapes are covered by ASME, again B89 1.9 standard, where allowance. So when you think of the gauge block sets, they are marketed with built-in wear allowance, and that allowance fails to use the true meaning of tolerance, because true tolerance doubles the amount, okay, like this, that the block can deviate from its intended size. So therefore, gauge block tolerance is not always equally split between plus and minus, okay? That's what's commonly used outside. So in the lab, we're using gauge blocks as standards and trying to calibrate the instruments by using the gauge block. But we also have to calibrate the gauge blocks. So calibration of gauge block, how are we going to do it? It's just a verification that the block is within the tolerance, again, specified in the previous table, okay? And then how is it done? By comparing with master standards of known calibration and known traceability to the national length standard. So every time we think about calibration, you are comparing your instrument, measuring instrument to a standard. So when is it done? Periodically according to a systematic program based on a statistical quality control, again, SQC, okay? Everything about checking up with the standard is under quality control. So not less often than annually for grade AA, quarterly for grade A, and also semi-annually for grade B. That's just like trying to tell you how we grade them, okay? So when required by visual inspection, ringability, ringing is nothing but you're adding them, like adhering them together, decline or slipping quality control level. So this is when we do that calibration on gauge blocks. So who calibrates, okay, working sets? So the user gauge department or any of the facilities for calibrating master sets, they're going to do that. And some smaller companies going to hire the consultants to do that, okay, for them. So who calibrates master sets? So independent, again, metrology laboratories. There are many companies only doing this measurement and calibration, okay, or standardization. Manufacturers or gauge blocks, they do it if they have the metrology person in the company. The NIST is your government, okay. Now, what is done with worn blocks? They are replaced. What is done with worn sets? They are regraded, okay, regarded for a lower level of precision. So in the lab, for the education purposes, all of our gauge sets are not calibrated. They're just used whatever. So the precision is all wrong, right? And okay, but it's just for education purposes for the students to just to take a look at it and touch it and be able to learn the method without looking for accuracy or precision out of it. Okay. Okay, so gauge blocks are used to calibrate other instruments. To ensure reliability, the gauge blocks should be sent to metrology laboratory for calibration if they show conditions below. So that's already explained right here with this table. So it shows normal wear when compared to post-calibration. There's something wrong with the block. Ringing becomes difficult. You can't stick to each other, okay? When you do the measurement, you gotta use a block and then stack them all together. And that ringing becomes very difficult. So at that time, you're going to have a very wide interval between the blocks, or separation will become bigger, and your error is going to be higher and higher. And so at that time, you definitely need to calibrate them. So an increase in rejects and reliability blocks are also suspected. So SQC is your statistical quality control, and guidelines are used to develop a calibration plan for each gauge block set in any manufacturing plant. I'm just showing you the general use of gauge blocks in this table, and gauge block terminology in the next slide. So let's just take a look at this table for this is place for gauge block measurement, and you're going to consider gauge blocks when we want to have precision increase, when we want the length increases or importance or reliability increases or skill or measure decreases. At that time, we consider gauge blocks. The general rule is nothing but you use the blocks for every measurement unless adequate reliability can be more economically obtained by another method. And this is just outlining for you the rules by precision, and you can read this. We're not really stressing on you to do the precision measurement. Therefore, you can just go ahead and read it one time, and that should be enough for this class. So gauge block application, we use gauge blocks primarily for comparison method of measurement. So to use gauge blocks in measurement, we need all four of them. First, to know how to handle and care for gauge blocks. The second is to be able to figure gauge block combinations. And the third is to be able to ring or adhere the blocks together or stack them up. And the fourth is to understand the principles of comparison measurement. Terminology is here in this picture. Then you can see the terms are used when working with the gauge block. So when you look at the gauge block nomenclature, is your terminology. First, you definitely need to know combination. So that's a group of blocks that form desired size when ran together. Series, all the blocks of one basic size. So when you look at the set, okay, your gauge block set in a little box, you're going to see different series are in there based on their sizes. And then ring is nothing but placing the blocks in intimate contact so their reference surfaces adhere to each other. Ringing interval is nothing but the separation. Those are micro separation between ring surfaces. Okay, so it's in between this block and that block. And then film is your air or liquid separating ring surfaces. So sometimes we use oil in order to get rid of this air or liquid in between them. So here you can see we stack the ring together in a combination. Where block is nothing but the blocks reserved for use as reference surface. Okay, thin block right in there. So block 0.100 inch or thinner series, really thin. A long block is something that you can really hold. So any block longer than 4 inches, okay, is called long block. Okay, we know how to calibrate, we know how to use the gauge blocks, so now we have to know how to care for them. So rules for gauge block care 1 to 7. So care of gauge block is important because what we're doing by carrying the block is to improve the reliability, speed of measurement, and also lower the cost of measurement. So the rules for gauge block care: never attempt to ring or otherwise use gauge blocks that have been in contact with chips, dust, or dirt-laden cutting fluids. Okay, before using, you definitely need to clean them with a high-grade solvent or commercial gauge block cleaner. In the lab, we use a lint-free tissue. We call that surface wipe. Okay, do not allow blocks to remain run together for long periods. Okay, you gotta separate them daily. And when not in use, place blocks in a safe place so where they will not be damaged, preferably in their case. Okay, that's how we store them. And before putting blocks away, make sure you clean the blocks and cover with a non-corrosive oil or grease or commercial preservative. That's definitely in a facility. Okay, in the lab we don't do it. Again, we're in an education institution, so therefore we don't really practice the facility, okay, rules. So be on constant guard for burrs, nothing but your scratches on the surface. So if anything has been placed on a block, or if it does not rain readily, use a conditioning stone. And I'm going to show you that stone later in the slide. Immediately. You have to do that immediately, okay? Otherwise, your calibration is going to go crazy. So thoroughly clean gauge block case periodically. Okay, that's what we have to do to care for the gauge block. So here's your stone. This is called a conditioning stone. It's pretty expensive, by the way, and it's used to rub the gauge block to remove your burrs and your nicks. So this care of gauge block supports, again, reliable measurement and long life of blocks. Okay, so you don't have to spend more money to buy again. wear blocks, the little thin blocks that we use. So wear blocks, both they are made in steel or carbide, another element from your periodic table, and they're used to increase the life of a set of gauge blocks. So they're used as reference again surfaces at the end of each block stack. Okay. Bringing gauge blocks, if two sufficiently flat, smooth surfaces come into contact. So you can see this exaggerated picture right here. You can see two surfaces come into contact. So they will adhere or ring. So ringing makes us easier to handle a stack of blocks as one unit and more. Ringing is nothing but like they come into contact uh, together, as as compact as possible. So you use the word adhere to each other, making the separation uh, small, okay, small or narrow, as much as you can do it, as much as you can compress the two surfaces together. So here you can see poor finish. Here you can see a little waviness. This is your liquid film. Here is your air film in between the two surfaces. And this is your run. Okay, so you can see the air, the liquid, the waviness, the poreness between the two surfaces is at minimum. You might say like, oh, run mean like a perfect contact, but actually it isn't perfect contact, but it is the best. Okay, it is the best contact. But you still have a little bit of air, a little bit of liquid, a little bit of waviness and poreness in between the two surfaces. So your air, oil, grease, and surface irregularities, okay, they hold the two surfaces apart. And they're definitely micro, okay, very micro. You can see by using your naked eyes at all. So here is your metal to metal surfaces, contact between the high points, okay, hold surfaces apart. Even heavy grease will not eliminate friction if surfaces are very rough. The next one again, metal to metal. Contact may be prevented by lubrication or air film, okay, for the wavy surfaces. Here is your liquid film, is your oil or grease. And they may hold the surfaces apart by several thousands, but they can be forced together to um, um, within a few million. Okay, so again, you cannot be able to sense it with your naked eyes. Air film will separate the surfaces until squeezed out, and the last few millions are difficult to move. Okay, you have to use precision instruments in order for us to be able to do that. With our hands, it's a bit difficult. Anyway, we do our best. So although apparently metal to metal again contact, some film definitely remains. So the theory of ringing is nothing but when two surfaces are brought together like this. So some space called separation is right here. See, these are called separation. Still exists between them. So we call this remaining separation the ringing interval. Okay, you can see it, but it's in between this surface and that surface. So without it, you will have just one solid piece and not two parts. So as long as you have two parts, you always have this remaining separation, and we call that ringing interval. Okay, without this interval, you would have only just one piece. Okay, so the theory of ringing is to explore why surfaces adhere to each other. So here in this picture, you can see the atmospheric pressure, okay, the ATM, we call it ATM, atmospheric pressure. We're all subjected to that pressure outside as long as you are stuck to the planet, okay? And causes the attraction adherence, which was later proved to be incorrect. So it is agreed that the cause of surface adherence or ringing is due to molecular attraction of surfaces. So you can see again at the molecular level, we have a whole subject area to study surfaces. So every time you want to study surfaces, you have to go all the way to chemical level, okay? Chemical and I would say like the molecular, the full quantum level. So between the big big molecules and small molecules, and we have the molecules that our instrument cannot be able to trace. Okay, so that level. So anyway, here in our class, we're going to stop at the molecular level, and the surfaces right here in this theory of ringing, they adhere to each other, and that's because the molecule attract to each other. Okay, molecule of this surface and the molecules on that surface, they have attraction. So attraction is nothing but they interact to each other, and at one point they blend. Okay, and we call that attraction, and because of that they adhere to each other. And we can go back to our system, our body system again. Everything inside is actually ringing to each other. Okay, they're not one piece. There are many different pieces, but they are adhered to each other. So that's how this complicated bio system is formed in our structure or in our body systems. And from their reactions, we get the structure that is completely you, okay, living, and it stays for approximately 70, okay, average 70, 60, and some people live longer than that, 100 or over, more than 100 years. So that's actually following the theory of ringing, just like we use a gauge block, telling the truth, okay? So all on your molecular attraction, making the structure as stable as possible. So here, when you look at the gauge blocks, are not in contact. So S and A right here, they're not in contact. The pressure, when you look at it, you're going to see the 15 psi. So that's your atmospheric pressure acts on all sides, okay? And they balance. So here they're separate surfaces. So in B, when you look at it, they are placed together. Okay, so the effects on the sides balance, but the pressure is now closed off here. No pressure, but you've got pressure here and pressure there. Pressure is nothing but you're forced, okay, on an area. Okay, so here is your area. Here, as you can see, only 2D, but then definitely there's an area right there. So the force on a particular area is your pressure. Okay, we're all subjected to that pressure, and we call that atmospheric pressure. And like I say, we're living in a medium. Okay, you are walking not through the air. The air itself is physical, and you are actually walking through physical particles, okay, and you're subjected to that pressure on your body surfaces. So just like that, the gauge block also is subjected by 15 psi in this example, atmospheric pressure, okay? So when they are attached to each other, the pressure go on the surface, outside the surface, and you're gonna get very little in between them. So when you get to C picture right there, okay, shows the blocks can resist about 200-pound pull. So that's pretty big force, okay, 200-pound pull is nothing but your force, okay. So based on the 15 psi atmospheric pressure and a block area, so when you measure it, you're gonna get 0.525 inches. The force holding them together, okay, is going to be 7.7 pounds, a far cry from the 200 pounds. So that's the amazing property of pressure and your force. And again, the adherence force or attraction, okay, in between these blocks, following this theory of ringing. Okay, technique for ringing gauge blocks, how are we going to do that? So first you're going to choose 2 blocks, and then you're going to slide one block over the other. So press together while sliding, okay, press on it here, and then press on the other hand here and slide it. And then you rotate it, and then you position until exactly on top of each other. So if you take a look at it in 2D, you're going to see here, slide, turn, or rotate, and then position on top of each other. So these are the steps need to be practiced to develop the feel for ringing. So when gauge blocks are run, the measurement can be controlled to million of an inch, okay, 0050 and then a 1. So to ring blocks, clean the surfaces, And then overlap the surface about 1/8 of an inch, okay, and then slip one over the other and press blocks lightly together. And then rotate blocks smoothly until they are fully mated, okay? So sliding the blocks together, push away again the dust on the way. Rather trapping them, we're pushing the dust out between your intervals, the ringing interval. So from the contact surfaces. So you will get better precision in your measurement. The stack of several random blocks is normalized with a single block of the same nominal length. So we divide the difference by 5 to obtain average ringing interval. So what we're doing right here is when you stack your blocks together, you're like ringing, okay, the blocks in order to measure something. You stack your gauge blocks, and uh, and that stack is normalized with a single block of the same nominal length. And then we're going to divide that difference by 5. So I'm going to show you how we do that. So here you can see, okay, this is just trying to show you about the heat sink, because every time you stack the block together, sometimes there's a heat effect from your hand, okay? So patient and a high application comparator, this is called a comparator, are all that we need to test ringing ability. We're just trying to see the ability of your blocks in ringing to adhering to each other. So the stack of several random blocks is normalized with a single block of the same nominal length. Okay, so the comparator is zeroed on a single block, okay, and the block is replaced with the stack. So the plus reading will be the total accumulated ringing interval, okay. So the ringing intervals are in between each block right there. So 1, 2, 3, 4 ringing intervals right here. And we can be able to measure by using a comparator, which is this one, and you can see and read the accumulated ringing area in between this, in between these blocks. Okay, we talk about stacking the gauge blocks to do measurement. So thus we call that combining the gauge blocks. So Johansson, his system allows many dimensional combinations. Okay, you can do so many combinations by using all of that block in the set. So combining for a given dimension, to select the blocks required for any combination, what we do is we eliminate the digits, usually from the right. Okay, so now we want to measure 24.817. So we're going to choose a block to measure this to give a a better precision. Instead of using other instrument, we're going to use a gauge block. And we want to measure 24.817. So we're going to choose the very first block is 2.007 block. Second one, because I've got my 7 at the end, okay? So we're going to eliminate 7, so that's 7. And then we're going to eliminate 1, which is 2.31. Second block has been chosen because when you look at it, 2.007, subtract that from the total. So the remaining length is 22.810. Okay, so when you look at it, the last digit is 1. So I'm going to go back to my set and select 2.31 block. And I'm going to minus that 2.31 block from 22.810, and I got 20.50. I go back to my set and select the last block, which is 20.5. So here is my stack. So I have 3 blocks to make 24.817 measurement. Okay, I have 20.5, 2.31, and 2.007 block. So if I put them all together and stack them and combine all of my 3 blocks, I'll be getting that measurement, 24.817. Okay, how do we go? Again, we go from the last digit, okay, and then remove it one after another. After removing, make sure you subtract that, okay, so you will get the remaining length here. If you don't subtract it, you're going to have a crazy measurement. So here it's just trying to show you how we select the block. So dimension of the block, arrange for easy selection, okay. The dimension desired, 24.817, and then the procedure to follow is nothing but elimination, okay. Elimination, the digit, again, from your right. This is just trying to tell you the same thing, alternate combination. Here again, we're doing 24.817. So your proof, doesn't matter how many blocks are you doing, got to combine all the way to 24.817 to satisfy that measurement. So here, alternate combination, you can use a standard block sets, provide great versatility in forming the combination. So to get 24.817 dimension, we're going to select the gauge block 2.007, 2.31, and 20.5 in the previous example and stack them together. And this one is just showing the forming combination with standard blocks to get the dimension 24.817. Okay, so it's about the same thing, but whether you're using 3 blocks or you're using more blocks, you will end up with the same total combination. Okay. Okay, here this is for you just to know. We don't have comparator or snap gauge in our lab, so therefore we can do this. So for you, if you can be able to read this and know that should be fine for this class. So dimension that cannot be combined directly. So at that time, for dimension that cannot be combined directly, we're going to use something called a comparator, and you have already seen that in the other picture, previous slide, okay, or a snap gauge. So combining to find the dimensions. In combining the gauge blocks to find the dimension, we use bridging method. Okay, bridging is doing nothing but we're speeding up the block selection. Instead of going and thinking about which block should I use to stack them, okay, we use a bridging method. And again, it depends on your experience on how to do bridging, okay? So you don't have to so stress out on this method. All you need to know is sometimes we use a comparator and a snap gauge when we cannot be able to combine the dimension directly. So here you can see a comparator here. So your anvil is right there and your block is 25.00 and that block is acting as an anvil. So here you can see from here to here is 25.036. From here to here, little separation is 0.036. So here I'm using 3 blocks. Okay, one is 23, second one is 1.030, and the third one is 1.006 in order for me to give the combined height of 25.036. Okay. When used on a snap gauge, the same thing. Here is my stack, and I am trying to get 25.036. So here is your gap, 0.036, and here is your block, 25.000 altogether. Okay. And the surface plate is right there. So use any combination of blocks making this dimension. You can either use this with that, or you can use the 3 sets right there. Okay, compare the same thing. You can use the 3 blocks a set, or you can use this and the comparator right there with this little gap. So that's 25.036. This is also 25.036. This block and that is going to give you 25.036. And here this stack is also giving you the same. Yeah. Okay, so going back to bridging. So bridging consists of choosing successive values on both sides of the desired unknown values because you're trying to get the value for the unknown thing. So bridging is to speed up your selection of your blocks. So what you do is you choose a successive value, okay, to make it easier. So in order to practice to learn the correct field and also to remember the effect of heat transfer from your hand, we use bridging. And you should definitely wear the insulating gloves. In our lab, we don't need it because again, it's for education purposes right here at school. But in real facility, you will definitely need to use insulating glove, especially when you go micro measurements. We don't want the heat because your blocks are very sensitive to heat transfer from your hands. Okay, we're thinking about your gauge block surfaces they are at the molecular level. Okay, these surfaces are the precisions are we can see with our eyes or feel with our hand. Okay, so therefore we have to follow the rule and be so careful about the heat transfer. So definitely recommended to wear, and they will make you wear it if you get the job in there. Insulating gloves and also plastic insulated tweezer. And we call going into the clean room in order to reduce the dirt and dust as much as possible. Okay, holding the gauge blocks with a hand is not very good. Okay, they mess up with your reliability. So therefore, we have gauge block holder for serious measurements. So different gauge holders are used. Again, this is wrong. It's supposed to be used again. So used for square and rectangular blocks. So the gauge block holders make it more convenient to use gauge blocks and more reliable measurement. So gauge block holders reduce, what they do is reduce heat transfer from your hands because your hand is not touching the blocks, so therefore you can get rid of the heat from your hands, okay, by using the holder. So they help minimize the negative effects. Temperature expansion can help on the measurement. So by removing the heat from your hand, what this gauge block holder is doing is to minimize the negative effect, okay? The temperature from that heat can cause on your measurement. So here is your stack of your block. So these are made of steel, okay? And the height is at 68 degrees Fahrenheit in this example. So you have your steel, aluminum, your zinc, and your tungsten carbide, okay? Different materials right there. So this is just exaggerated drawing showing the effect of temperature changes on the measurement. So here is an example of a gauge block holder. As you can see right there, and it's holding a stack of blocks, okay? So here you can see your end standard. That's nothing but your standard block. And then your end screw is nothing but here to hold that stack. And you also have a square block in between them. So this pin gauge assembly showing the use of a square gauge block holder, okay? So the holder of a square consists of expandable rods, and that pass through the center. You can see the hole right there very clearly of the block. And to measure reliably, ring the blocks fully with the end standards, assemble the stack, okay, with the tie rods. So this is your tie rods, and firmly draw up the end screw right here with a torque screwdriver. He's got the screwdriver in his hand. So anyway, that's how you use your square gauge block holder. Rectangular gauge block holder is a little bit different. So these are holders for many measuring instruments that you can see here, scriber dividers and a snap gauge. And other holder you can see right here, another example, use a telescoping channel and which slide together then apart to provide a wide range of sizes. And sometimes you can see the heat transfer can be minimized by channel air, okay, circulation. Just trying to cool your hand down, okay? If you don't know how to look at it, you can look at the metrological feature right there. So here we can go a little measure plane is right there. The line of measurement is right here. The reference plane is right there, okay? And this is your force line controlled by the maximum finger torque right there, and your force applied at the center of blocks along line of this measurement. So your blocks are right on this line. So when you look at the functional feature, you're going to see your exposed end right there. So that's your end standard, okay? End standard always come at the end. That's why we call it end standards that you use to ring the blocks together. And extension channel is right here. And the force applied from both sides. So here you can see your hand on both sides. And then the clamp swings open. And your locking holes is right in here. But you don't have to know everything, okay? All you have to know is this is how the rectangular gauge block holder looks like. So coming back to end standard, so they adopt the gauge block reference surfaces to part feature. So reason for end standard, so you can see right here your axis of instrument, and here is your line of measurement. Okay, here axis of instrument and line of measurement is now overlapped, okay? So when the outer ends of the end standards are exposed, inside measurement can be performed in conformity with your Apes law. So don't forget your Apes law. So end standards gauge block present only one type of reference, and we call that the May reference plane or May plane. Okay? So May plane are used to measure outside part features. For inside, we use the female lines. Okay, female lines are not May planes, and they're used to measure the inside dimension. So here you can see the gauge block provide male reference plane, but the May part feature requires female reference plane, and we call that actually line. Okay, require May line reference, and here require the angular reference surfaces. Okay. And here is your spherical surfaces and line intersections, and scribe lines require point references. A little bit difficult to see right here. So anyway, it's just a matter of the terminology, but for our textbook, it's going to go with the May plane and female lines. But here in this example, they're going with the May reference plane, and they sometimes call the May part feature as a female reference plane. And then require here, it's just trying to show you the IDs require the May line reference. So don't get into confusion, okay? You don't really need any of that. All you have to know is for end standard, okay, you need a line of measurement. And that line of measurement can be a reference. And that reference is either male or female, plane or line. And that's okay. But for male, we go by outside, and female is for inside dimension. I was just showing you, okay, different shapes of your block, and the first one is here, and that's just a base block. Second one is right there. You have a little ball end standard. Okay, this is your ball end standard that we use at the end of the stack. And C is your foot block. It definitely looks like a little foot. And D is your center point. F has a hole in the center. And also look at the shape. It's a little bit different, yeah. And your E, when you take a look at it, it's called the scriber. See how different the shapes are. And then your F is your 1 inch and standard, another end standard. And G right there, that's your 3 inches extension caliper bar. And then your H is a 1 inch extension caliper bar. And then your R is right there, 0.450 end standard, another end standard. And then your J is your trauma point. And then your K is your 1 inch extension knife edge caliper bar, okay? Principle used for gauge blocks, the calibration or other instruments, we use a gauge block, and lesser standards. To calibrate the lesser standards, we use a gauge blocks. Setting of comparators and indicator type instruments, we also use the gauge blocks. We use gauge blocks in attribute gauging. We use gauge blocks in machine setup and precision assembly. We also use the gauge block in your layout, okay? So for setup, gauge blocks they're totally recommended. They're widely used in the manufacturing facility for fast and accurate setup. So here, see, he's measuring from here, this way to that way. We want that much of length, and he is setting that up. And the one important caution is that gauge blocks are never used in this manner without wear blocks. Okay, sometimes we use assistance of the wear block in order to do the setup. So it takes a long time to make measurement with gauge blocks, but when the blocks are used, you get precision. You also get accuracy, and reliability come a long way. Okay, so gauge blocks are used to check spacing relationship here before operating a machine. So here, just giving you an example of your direct use of gauge blocks. So direct application of gauge blocks to set the desired dimensions, eliminates errors from transfer of measurement. Gauge blocks we widely use them with sign bars and sign plates for angle measurements. And that we will come into into all of that in details in chapter 12. So we use gauge block in attribute gauging. Okay, so gauge blocks within standards and holders, they are valuable as attribute gauge. So the most important reason is that they eliminate one or more intermediate steps, okay, between the gauge and the standards. Another reason is that one set of blocks and standards and holders can be made into thousands of gauges, okay, saving tremendous inventory. So that's the advantage of using gauge blocks for attribute gauging. So attribute gauging is nothing but just a sorting operation, okay? Not a function or methodology, just an operation. So we use this operation in production processes along with the inspection and quality control. So we're doing nothing but using attribute gauging to do decision making, okay? So the decision is merely whether the part is good or bad, or we try to decide whether it is a go or no go for an operation, okay? So here you can see a go and no go gauges. So here, if you get this measurement, that's okay, accept it, and if you get this one, it's not okay and don't do. And you can quickly use this, okay, into sorting out some operation. So here, no go, no go, and here there's like go, go, meaning like accepted measurement and not accepted measurement. And you can flip and use this gauge block and speed up measurement, yeah. And we definitely use it in quality control inspection. Here is another example for the direct use of gauge blocks for attribute gauging. So manufacturer can save on cost, again, all the time cost. So when they use gauge blocks, okay, so therefore they use a gauge block in order to reduce the cost. So direct savings are important, but indirect savings are also important. Indirect savings are even actually larger than direct savings. So as shown in the advantages of attribute, okay, here are advantages of gauge block for attribute gauging. So A, B, C, and D. So when X tolerant is in this range, when X tolerant is decreased to this range, then you do that. So when X tolerance is decreased to this range, again, you do this. So when X tolerance is this, but steps are eliminated, and then you're going to do this. Okay, this is just an example of how to use a step gauge in attribute gauging. Okay, so the next one is your recalibrated indicator technique. It's nothing but just a technique, and we use it in dial indicator and then interchange instruments. So interchange instrument is nothing but your instrument following the interchange method. So an N standard, again, that little block is needed in this method to hold the dial indicator at the right angle to the reference plane and a distance from the plane to permit your zeroing. Okay, so here is your reference plane, and here you have a gauge block 40.00. So that's a 40.00 millimeter end plane, and here is your dial indicator, and it's landing on the surface plane, reference plane, 90°. Okay. So for pre-calibrated indicator measurement, an N standard again is needed. So okay, that will hold a transducer at a right angle. Okay, this is your transducer, and that N standard is holding it at right angle to a reference plane and at a suitable distance from that plane to permit your zeroing. Okay, so to zero the indicator, any reference surface can be used. Zeroing the indicator is calibrating a point in space. So if mechanical indicators are used, both right and left-hand side mounted brackets are required. Okay, so this is simplified for remote reading of electronic and pneumatic instruments. So just trying to tell you, so front mounted assembly, you're going to do like this, and here is your block. So that's your block standard. So side mounted assembly, you're going to change, okay, this mounted position is completely different from the front mount. So because it's a side mounted, okay? So here you can see this is front and here is your side mount. and the same block, okay? And the last one, the gauge block, is right here. So that's called end mounted assembly. How are you going to mount your gauge blocks? You can do it front, side, and end. It doesn't matter what mounting assembly is, okay? To zero the indicator, any reference surface can be used. And the zero in the indicator is nothing but you are calibrating, okay, a point in a space. Okay, so the method is very simple. What you do is you stack the blocks on the reference surface and then you get the length. And gauge blocks provide million of an inch accuracy, okay, and can be constructed in thousands of standard components. So that's its power of gauge blocks. Again, their precision is in thousands of an inch. So here you have a 1, 2, 3, 4 simple steps, and that's going to provide a nearly limitless range of gauges with micro-inch accuracy. Okay, so here first, assemble your gauge without any gauge blocks. This is your zero indicator. Step 3, separate gauge. Okay, you're going to add the blocks for desired dimension, whatever you're measuring, and then reassemble. So here, going 1, 2, and then edit. Here, you're setting the 0 to start adding the block. Okay, here there's no gauge block. Okay, here we start to add. So you can see these colored blocks are added blocks. And the third one, you're going to inspect the parts, as any deviation from gauge block length can be read on the indicator. Okay, so every time you stack it here, you can see your little hand is now moving from 0 all the way to here. Okay, and this is called your pre-calibrated indicator gauge. The calibration is already pre-calibrated, and we're using an indicator, so it's easier, okay, for us to be able to read the measurement. So in recalibration, extend, okay, bar, extend bar. So here, extension caliper bar can be used with the instrument to see if it reads 0. So here, an extension bar is inserted to recalibrate the gauge. You can also use the and standards and the holders again and recalibrated indicator technique. Okay, same as the other technique. By using the holder, you will get rid of all the transfer heat. By using the and standards, you can be able to measure against that reference plane. Okay, so the use of standard holders and standards give great versatility to the pre-calibrated indicator technique. So the effective height, okay, in this example is the length difference between the stack A, which is this one, and then B, which is this one right here, gauge block stack B. So therefore, this method can be used for dimensions that are ordinarily too small for gauge block methods, because the holder definitely helps a lot, and also the end standards. Okay, and this pre-calibrated indicator technique, we use it for inside measurement. We also use for outside measurement, but in this textbook they only show for inside measurement. But again, we don't have to go into details. You only need to know, okay, about the technique. So it's been 0 in the illustration right there. And here you can see this is just trying to show you your extension caliber bar, okay? And this is your channel, and that's your base channel, and this is your base block. And here is your other base channel, and then your extension channel right there. And then with your end mounted assembly is right in here. So gauge blocks will be inserted in one or both stacks to create the desired dimension. Okay, so the extra step, of course, somewhat reduces the reliability. Okay, so this is all about the development, okay, and your gauge block. But in the lab, we're not going to go into details.
we're just going to use the gauge block as a standard, and then we're going to do one example on this textbook chapter, and to measure with the gauge block, and also the ringing technique is what we're going to do in the lab. Okay, that's it for chapter 8.